Hello and welcome to Data Science in Industry vlog. Today I would like to tell you about anomaly detection. This is the important topic in the field of Industry 4.0. Operators, dispatchers, maintenance teams, they would like to know if the technological process operates in a strange way. So it behaves in a different way than normally. It could be a potential state that will lead to the failure. It could be the early symptom of a failure. If we talk about the anomalies, we don't know what it is, but there is a risk that it is something bad, and we should pay a special, we as the operators and dispatchers, we should pay a special attention and check what is different than in a normal day, than normality. It could be even something good. Maybe the optimizer pushed the technological process to a new operating point with better efficiency, lower costs. This is also an anomaly from the historical data point of view, because this is a new way how the technological process is operating. But in many times it could be something bad. Higher vibrations, higher oil temperature. It's probably related with some kind of a failure. If we can name this failure, we will talk about failure detection or failure prediction, and this is the part of the predictive maintenance strategy, usually to predict the early symptoms of a failure or to predict the state that leads to the failure. But it will be covered in the next video. Now we will assume that we are not able to name the failure. We are not looking for a particular failure, for early symptoms of a particular failure. We are solving more general task, or just finding anomalies, finding things, values of parameters that do not fit to what we would call a normal process behavior. So let's take a look what is the anomaly detection. The anomaly detection is the process of identifying unexpected items or events in the dataset, which differs from the norm. We can identify three types of anomalies, three categories of anomalies. Those are the point anomalies, like this one. So here we can see that there is a single instance of data that is anomalous. This point is far away from all other points, from the rest. It's a clearly we can see it's an anomaly. Maybe it is related with sensor failure or sensor calibration, but this is the point anomaly. We also have contextual anomalies, where the anomaly, like here, is context specific. So we usually see such anomalies in time series. Those particular values here and here are, let's say, okay for these parameters. There are even higher or lower values of these parameters. So if we just check minimum and maximum limit, we would say that it's the reasonable value for this parameter. But looking on its neighborhood, looking on the data on the left and right, we can see that it differs. We would not expect value here and here, right? So that is why we say it's an anomaly. So the context here is important. We can also talk about collective anomalies. It's here, right? So there is some pattern, and this bump looks strange. It's not a sinus-based pattern. It's a rectangle. It looks strange, right? And that is why we will call it an anomaly. So to detect such an anomaly, we need to see the whole data to check that this guy here differs from the rest of the data set. So as you probably understand, this type of anomaly is the hardest to detect, but there are, of course, methods to handle this. Okay, and let's move forward. What are the challenges in anomaly detection? Well, first of all, we need to check that something differs from normality, from the normal behavior. So we need to define what is the normal behavior, what is the normal temperature of the oil, what is the normal flow of the fluid for a given process operating point, for a given context, for a given device load. So the accurate representation of normal behavior for each parameter is very challenging. There are a lot of disturbances that affects our technological process. There is noise associated with measurements. The control system causes some oscillations. This is the important challenge to define what is the normal behavior. Then, if we would like to check that there is an anomaly, we need to think which parameters should be used in such assessment. So what kind of features we should use to define normality, the normal profile, normal behavior of a system. All the vibrations that we are measuring, or the average level of vibrations, all the temperatures and pressures and flows, or just the selected parameters related with a particular aspect of the technological process. This is also a challenge, and we need to understand the process, the physics, the control system behind this device in order to properly select those features. Then, if we have this normal behavior and we will detect that something differs from this normal behavior, well, we need to find where is the threshold, where is the border between a normal behavior and the anomaly. Because maybe something differs from normal behavior, but just a bit. It's a small difference. Should we call it an anomaly or not? The border is not very precise. We need to assume that this border is somewhere, but it's also a challenge. And we also need to understand that industrial processes, devices, are changing over time due to the device wear, due to the service actions, part replacement, fuel properties changes, outside temperatures and humidity, so the external condition changes, etc., etc. So we should create an algorithm that adapts to those changes, because our definition of normality, of normal behavior, changes over time. It's evolving with the system, with the technological process. If we create an algorithm that will simulate the normal behavior, so the algorithm that will predict the values of process parameters, assuming the normal state, normal behavior. And we will use this algorithm to detect anomalies in 1, 2, or 3 years. Probably it will not gonna work. So the current definition of normality will not be up to date in 2 or 3 years. The process will operate in slightly different way than today. So our definition of normal behavior also needs to be updated once in a while, or we can try to apply some adaptation mechanism that will adapt the algorithm on the fly. And the last challenge is the availability of training and validation data. So the availability of data related with the technological process, with the device. In many times, we are asked to develop and implement the anomaly detection algorithms before even the plant or factory is constructed. So the system must be prepared to detect anomalies. This is the extreme case, but there are such cases, and there must be some algorithms that will installed or prepared to be installed, that will detect anomalies by just comparing the typical distribution of process parameters with current measurements. Typically, we can have 3 cases. This is a great picture taken from the Goldstein and Uchida paper about anomaly detection algorithms. So thanks, and I will use it for this presentation. So in the first case, we have data provided by the plant or factory where we have labels that says it was a normal process behavior or there was a failure or a particular type of a failure of an anomaly. So it's rather related with the failure detection and prediction, but still someone can say it's an anomaly, and here this is the normal process operation. So we have those labels. And if the number of points that are labeled as anomalies, if the number of such points is high enough, we can try to perform to develop the classification algorithm, right? Of course, the majority of data would represent a normal behavior, so it would be unbalanced classification task, but there are ways how to handle this, and this is I would say the perfect case for us, because in this case we'll just try to use the machine learning approach, supervised approach, the classifier that will try to find some patterns in the data, the pattern that is associated with anomalies. It is really hard to find such a case in reality. I had it in just one project. In most of cases, we have this case. So we have the data taken from the plant, and the majority of data, 99.9%, of data represents the normal behavior. If there is a failure, if there was a failure, right, or something strange, usually it is there is some comment in the operator notebooks, in the dispatcher's notebooks. So we can identify points associated with normal behavior, or we can just assume that, well, if the majority of point, like 99.9% of points comes from the normal behavior, we can assume that more or less all of them are represent the normal process behavior. Using this data, we can try to create so-called a digital twin. I don't like this name, but people like to use it, the digital twin. So we can try to create a model of a process, or model of part of the process, the prediction model of some parameters that defines this anomaly. And if we have this model that simulates normality, we can compare the model outputs with current values of parameters, with the sensor values. And if there is a difference, significant difference, we can say it's an anomaly. So we can try to infer about the anomaly based on the differences between model outputs and measured parameters. We can also have such a case, so totally unsupervised approach, where we really don't know if those points comes from the normal process behavior or the anomaly, or even there are no points yet because the plant is under construction. In such a case, we can apply some anomaly detection algorithms that are based on inner relations between parameters, on some patterns, distributions that are related with process parameters and relations. If we can see that the normal relation between parameters is missing, there is something strange with this relation, we can assume it's an anomaly. And I will discuss such algorithms, unsupervised algorithms, in this presentation. The simplest approach to detect anomalies is to use some statistical measures. If we have a parameter, it has different values, so all those data points have some distribution, and we can take the box plot, which is the summary of let's say, this distribution, and we can use some of the parameters, statistical parameters, to detect if there is an anomaly. For instance, if the new value is higher than maximum or minimum value so far, we can treat it as anomaly. But also we can take the 1.5 of the interquartile range, and if the value is if the new value is higher than this interquartile range plus minus 1.5 multiplied by the length of this interquartile range, then we can say it's an anomaly, right? Or we can use our own threshold. It can be a 95th percentile or the 5th percentile. What is the interquartile range? Maybe I should define it. This is this box. So it starts on the 25th percentile and ends on the 75th percentile. So 50% of data is here. All right, so this is the very simple approach. We can also perform some statistical tests, like, for example, the groups test. Of course, it's rather for a single parameter, right? It's not if we have a process that is described by many parameters, it would be hard to apply such an approach. But if we have just one or two parameters and we can treat them individually, independently, why not? This is one of the options. There are some methods that are based on distribution. So we can try to fit distribution. Maybe the normal distribution will be okay, but we have to check it. There are dedicated statistical tests that checks if the data has the normal distribution. If so, we can fit the normal distribution. If not, we can try to fit different kind of distributions. And when we have the distribution, we know what is the probability of having a particular value of this parameter. So when we have a new value from the control system, new value of a temperature, pressure, or the flow, we know what is the probability of having such a value, assuming we have some particular distribution of data. If this probability is low, and once again depends where we set our threshold, but if it's low enough, we can say it's an anomaly. If we have once again, this is good for a single parameter, but if we have more parameters, especially more dependent parameters, we would have to use the multivariate distribution, like, for example, multivariate normal distribution. So there are many distributions we can use, not only normal, the Poisson or exponential function should also might also be useful, or many other functions. You can check different distributions, then see your data distribution and try to choose the best one. Sometimes we can do some mathematical transformation in order to obtain a desired distribution. Like if the data are positively skewed, then we can try to make the log transformation. If the data are negatively skewed, we can do the exponential transformation in order to get the normal distribution, right? Okay, so this was based anomaly detection method, distribution-based anomaly detection methods, and now let's take a look on distance-based anomaly detection methods. So here we are not focused on the distribution, but rather on the distance. So if we have a new point, let's say this operating point is described by two parameters, let's say temperature and vibrations level or flow. Okay, the temperature and flow. We can check how far is this point from other points measured in the history, measured, I don't know, last week, or measured for current device load, depending how we will define our context. But we have a set of points. Those points comes from the normal process operation, and this point is probably the anomaly, because the distance to the center here, or to the nearest point, we can define different measures, is higher than, let's say, to the center is higher than some threshold, some radius. All right. One of the very popular algorithms is k-means. This is the clustering algorithm. And this is in fact what we would like to do. So we would like to find clusters of points and then check if a new point fits to the cluster or it's an anomaly. So this method that uses the k-means algorithm clustering approach is a density-based anomaly, so the anomaly detection method. So now we are focused not on, well, the distance, yes, but also the density of points. So there is an assumption that points that are close to each other creates a cluster, right? So this particular cluster might be related with low device load, low unit load, low boiler load. This particular cluster might be related with high device load. This particular cluster might be related with some other configuration of a device. And we have data that comes, in this particular case, from the low device load. So they come from the control system, and they were measured when the load of the device was low. Right? They are here. And we can use the clustering algorithm to detect our clusters. Here we can see that the algorithm detects 3 clusters. They have different colors. Now we can try to define boundaries of those clusters using distance or percentile distance. For instance, the border can be set on the 95th percentile from all distances between data points and their clusters and their respective clusters centers. So we have distance from this point to here, distance from this point to here, distance from this point to here, all the points from this cluster. We know that what is the distance to the center, and we can set up the border on the maximum distance or the 95th percentile of those all those distances. Depends on our threshold. And then if we have a new data point that comes from the control system, comes from sensors, IoT platform, whatever, we can calculate its distance, like for example this one, the distance from the cluster center. If it's higher than our boundary, our maximum distance, then we can call such a point an anomaly. I mentioned about the k-means clustering algorithm, so let's briefly see how it works. This algorithm, the goal of this algorithm is to find groups of similar points. So first of all, we need to define a priori what is the number of such points, of such groups, of such clusters. This is this k parameter. If we will assume that the k equals 3, it means the algorithm will try to find 3 groups, 3 clusters. In this particular case, it's quite easy to assess that we should have 3 groups. But if we have more data and more dimensions, more parameters, it's not obvious to choose the proper number of clusters. Probably we'll have to try different numbers, as well as there are some methods that help us with such assessment. Okay, so let's stick to the simple example. Here we can define that k equals 3. We have 3 groups. This algorithm is based on the distance. If the distance to 2 points, let's say this one and this one, the distance is big, we can say that those points are not similar. But if the distance is small, like this, 2 points, we can say that the points are similar. So at the beginning, the algorithm makes the initialization of centroids. It can be a random initialization, so it will place some virtual points that represent centers of the cluster of the group. So it can be put, one can be put here, one here, and one here. Why not? It's a random choice. Here we can see that one of the virtual center of the centroid of the first cluster is here, the second one is here, and the last one is here. Next, for each point, for each data point, we checks what is the distance to all the centroids, and we assign a point to the group based on the minimum distance. So if the distance from maybe this point to this virtual center, to this centroid, is the lowest one, we will assign this point to the green cluster, right? Because the distance here is the closest. This point here has the minimal distance to red centroid, so we will assign this point as red. It will belong to the red group. When we assigned all the points to a particular cluster, then we need to update centroids. So take a look on the green group. For this group, we can calculate where is the new center of this cluster, right? For sure, this center is shifted towards this big group. We just have 2 green points here, so we can update the centroid position. Let's say probably to here, right? And we can do it with all the centroids. We'll update that the red one will go a little bit to the right, the blue one to the bottom and to the right, right? And when we update centroids, we need to once again assign all the data points to to groups. So those points here will be now a blue group points. They will belong to the blue cluster because the distance to the blue centroid is the minimal, right? In comparison with the red centroids and yellows and green centroid. After we assign all the points to new clusters, once again we have to calculate the center of those new groups, and so we need to calculate new centroids and once again update all the data points, calculate what should be the label of those. Well, label, maybe not, it's not the a good word. How we should assign every new data point to a cluster. We should stop this we should stop those iterations after there are no more changes of a centroid, right? So if we see that all those centroids are stable, are not moving anymore, it means that we have that all the data points are assigned to the clusters, like here, right? That this algorithm can be stopped. So it's a widely used algorithm, very simple, yet still efficient. The crucial thing here is to choose the proper number of clusters. We can also use different density-based anomaly detection methods, like, for example, local outlier factor method. Local outlier factor algorithm is also based on density. So I will not go down into the mathematics, but the idea behind this algorithm is that if you have a point, let me just put the pointer. If we have this point here, we are comparing what is the density of points around this point in comparison with density of neighbors, nearest neighbors of this point, right? So what are the nearest three, let's say, neighbors we can choose? 2, 3, 4. What in this particular case we will check 3 neighbors. So if we have point P1, the nearest neighbors are S1, S2, and S3, and we are, comparing the density, the distance to other points for each particular neighbor, and for P1, how far is it from its neighbors. And if the distances between points for the nearest neighbors is lower, essentially lower than the distance between our points and its neighbors. So the density around P1 is lower than the density around its neighbors. Then we will say that P1 is an anomaly. The way how we calculate it, it's a bit more complicated, but still it's quite simple. But this is the idea behind this algorithm. If the density, if the score calculated by this method is around 1, it means that the local density for our point is similar to its neighbors. But if it's higher than 1, essentially higher, then the point of our interest is an outlier. Quite useful method. I like to use it in my projects. Here we can see the comparison of different methods, because of course this is just a selection of methods. We can use also the one class SVM, isolation forest. There are many methods. I present just a few of them, but I would like to stress the fact that the outcome of the algorithm depends which method you will choose. So if you choose the one class SVM, you will get the different clusters, maybe not cluster, different. You will find different anomalies, than if you use a local outlier factor, right? So for each particular project, I recommend you to compare different methods of detecting anomalies and choose the one that fits, that is the best to your particular case. Now let me present the local density cluster-based outlier factor method. Here is the interesting case. You see, we have three clusters, C1, C2, and C3. There is a question mark, if this is a cluster or this is a group of anomalies. 3 points that are anomalies. So this is the matter of our assumption. Is it a normal process behavior or is it an anomaly? Like I told you at the beginning, it's a challenge to define those things. We can see two obvious anomalies and 1 point. We are not sure if it's an anomaly or not. We can assume it's an anomaly. Probably it is. But also we can say it's a normal behavior. Right now we will assume it's an anomaly. But if we will take the distance from this point here or from this point to this one to its neighbors, it would be, well, similar to points, to distance between points in this cluster. So if we will assume similar density as in cluster 1, we would not call it an anomaly. We can call it an anomaly because we can see its closest context, because we are comparing the distance from this point to its neighbors based on the so we are comparing the density around this point and around its neighbors. So we take into account local neighborhood of this point. Keeping this in mind, then we can say it's an anomaly. And so this algorithm, this LDCOF algorithm, takes this into consideration. How does it work? First of all, we need to find those clusters, using, for instance, k-means algorithm. Then we can calculate what is the mean distance of points to the centroid, to the center of cluster, for each cluster. And then if we have a new point, we can assign it to the nearest big cluster, and there is a question mark if we can treat this one as a big cluster. Depends on your assumptions, depends on the parameter that you will choose. Okay, so if we will take x3, the closest cluster to x3 is C2. It's a big cluster. Then the anomaly score for a given point, in this particular case for x3, is calculated based on the distance from assigned centroid. So the centroid of C2 is somewhere here, divided by the mean distance of training points. So if the distance from x3 to the centroid is essentially higher than the average distance of other points, then we can say it's an x3, it's an anomaly. So the locality, the closest context of this x3 point is taken into consideration in this method. Another approach, very popular in healthcare, in biology, in bioinformatics, but also very useful here in anomaly detection, is utilization of PCA. Especially if we have a lot of parameters, our process is described by a lot of parameters, it's hard to say which one is the most important, which one should be taken into consideration. We can try to reduce this dimension by using the PCA method. It's just linear. I talked about this method in one of my previous videos. It's just the linear transformation of the data set. We transform the data, linearly transform the data, and looking for a new coordinate system. And with this new coordinate system, we can describe the variation in the data with fewer dimensions. So this is a very simple example. This is our original coordinate system and the data. We transform it, so we have a new coordinate system, right? And you can see that the first dimension in this new coordinate system, we call it the first principal component, can describe, well, around, 80-90% of variation in the data. So if we know what is the first principal component of each data point, we can tell a lot of this data, right? And of course, if you take the second principal component, we know everything about the data. But the goal is to focus on first principal components, first few dimensions, because they describe a majority of variation in a data. Let me give you the example taken from the real-life project. This is the turbopump. It was, or maybe it still is, working in one of the power plants. It is described by 35 parameters: water flows, inlet pressures, inlet and outlet temperatures, temperatures and pressures before and after the turbine, vibration of bearing, temperature in various parts of the pump housing, and differential pressure across the seals. So a lot of parameters, and it would be hard to see all of them at once, right? And that is why we try to reduce the dimension by applying the PCA. In this particular case, anomalies was labeled, so the green data points here represents the normal operation, and the color different than green represent an anomaly from the history, some kind of a failure. So you can see that if we take the principal component 1 and principal component 2, so the first slice of this new coordinate system, we can see that there is a group of yellow points, right? And those points are associated with some kind of a failure. So instead of looking at temperatures, pressures, vibrations, all those 45 parameters, we can do the linear transformation and reduce it to two new parameters that are the linear combinations of those 45 parameters. And using just two parameters, we can see that there is a group of points associated with a failure. So if there will be a new point, and it will be somewhere, let's say here, we can say it's an anomaly. Or if we know the name of this failure, we can say probably it's the early symptom of a failure. Here, if we take the next slices, if we take a look on the plot or scatter plot of principal component 3 and 4, we can see another group of points, another cluster of points associated with a different kind of anomaly, with a different kind of a failure in this particular case. So if there will be a new data point, let's say here, we can say it's an anomaly. It's not a normal process behavior. And still we don't have to, separately analyze each particular parameter. We can focus on those principal component 3 and 4, which is also some kind of a linear transformation of all the parameters here. And on the end, we can develop a digital twin. I will talk more about this in the next video, where I will talk about failure predictions, about detecting early states of a failure or early states or early symptoms of a failure, or detecting states that will lead to the failure in the nearest future. Then building such a digital twin, such predictive models, is very useful approach. Here we can also use it. As you remember, when I was also talking about the digital twin in this video at the beginning, we can take all the data that comes from the normal operation, and we can create a model of the normal process behavior, right? So let's say if we have 2 or 3 or 4 important parameters, important outputs of our process, we can try to model the values of those outputs based on process inputs. And then if we will check that the model output differs from the real measurements, the estimated temperature on the outlet will differ than measured temperature, then we can say it's the anomaly. Of course, the question is what kind of parameters we should take into consideration, we should consider in our digital twin. I will talk. Here is the example of the coal mill. I think I was talking about this coal mill, but if not, please imagine that there is a coal mill, the crucial device in the power plant. It grinds the coal, and we can. This is a very, very important device. If there is a problem with this device, the unit load should be reduced. Sometimes even the problem with the coal mill generates a unit trip, very costly failure, very costly situation. So in order to detect the anomaly, or in fact in this particular case to predict the failure, to detect the failure, early symptoms of a failure, we made a digital twin that predicts the current consumed by the coal mill based on tens of inputs. And then we are comparing the mill motor current with the real measurement. The real measurement is marked here in blue color. The red signal is our estimation, the estimation of a digital twin. And if the difference between those two signals is high, we can tell the operator that there is an anomaly. All right. In this particular case, this anomaly is related with the fact that there was not enough coal in the mill, so the mill current consumed by the mill motor was decreased in comparison to the normal behavior, normal typical process state. Probably it was the reason. So probably the reason for this lack of coal in the mill was the feeder blockage. It's hard to say because there are no measurements. We are not measuring the mass of coal that is fed to the mill. That is why such algorithm can really help the operator to decide what to do. Because if there is a risk that the coal is not coming to the mill, then the operator should switch the mill to a new one, to the one that is waiting for such situation, or to reduce the load of such a coal mill. He has time because we can detect such a case 10, 20, 30 minutes before the real failure. So there is time to take some action. So building a digital twin, it's also a way how to deal with anomaly detection. And like I said, I will talk more about this topic in the next video related with predictive maintenance and failure prediction. Thank you and have a good day.